Woohoo! Welcome back. Tonight we're going to be talking about a little bit of bonus math involving something called the binomial theorem and Pascal's triangle. So we're going to start with the idea of Pascal's triangle. And so this is a triangle which at first maybe looks a little bit like, oh my gosh, where did these numbers even come from? But the really cool thing is you can generate this triangle on your own. The pattern is fairly straightforward. You start with, and don't worry about these things over here. So let me cover this up so we don't have to worry about that right now. And for this triangle, we start with 3 ones, 1, 1, 1, and then add the ones to get this 2. So we're going to start with the 1. We're always starting with the 1. You can see the ones to the left. You can see the ones to the right. And so I go 1, and then I add these 2 numbers together, and I get a 2, and then I end with a 1. For the third row, I have a 1. I add 1 plus 2. That gives me 3. I add 2 plus 1. That gives me 3. And then I end with a 1. For the next row, start with 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. End with a 1. So for the next row, I would start with a 1. The next number, what would that be? You got it. That's a 5. 1 plus 4 gives me the 5. Then the next number, 4 plus 6, is 10. And then it repeats, go in the opposite direction. So each row is a palindrome. So 6 plus 4 is 10. 4 plus 1 is 5. And then I end with the 1. And we could keep going. So the next one would be 1. You got it. 6, 15, 20, 15, 6, and 1. Come on, move over. And so on. So Pascal's triangle is hopefully it's a pattern that you can learn very easily, and you don't have to have it memorized. You could if you felt like it, but it's easy to generate the triangle. You just got to remember that initial 1, 1, 1. Now, how can we use this triangle? Well, we're going to use it today for the expansion of binomials, right? Binomials. And the expansion of when you are squaring and cubing and fourth, and et cetera, et cetera, et cetera. So, how does this work? Well, the first, and I can include this, a plus b to the 0th power is 1. So that's the very first row. Then a plus b to the first is a plus b. If there's a 1 there and a 1 there, those are the coefficients. And now what you may remember, a plus b, the quantity squared, this is something you memorize, right? It's a squared plus 2ab plus b squared. And the coefficients are found right there. So there's the 1, a squared, plus 2ab plus b squared. Now, how does this pattern go? Well, you follow the coefficients, but then you notice that a starts out squared, then a and b both show up together, and then b is squared. Let's follow this pattern for the third row. So the third row, or actually technically it's the fourth row, sorry, because of that 1 on top. But for the cube row, the coefficients are 1, 3, 3, 1. So I'm going to take a plus b, the quantity cubed. So this means a plus b times a plus b plus a plus b. It's a real pain to actually multiply this out. But if you know Pascal's triangle, then you follow the pattern. The coefficients are 1, 3, 3, 1. And then the other half of the pattern is that you start with the a, and you have a b cubed. And then you bring a down by 1 exponent. So a cubed goes to a squared in the next term, and you bring b into it. So you've still got 3 A cubed is AAA. This is AAB. There are still 3 variables here. Then A goes down by 1, B goes up by 1. So A squared becomes A, B becomes B squared, and then A finally falls out and B goes up 1 to B cubed. So next row, A plus B, the quantity to the 4th power. Again, the coefficients are 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. You start with A to the 4th. Then it's A cubed times B, A squared, B squared. A keeps decreasing the exponent. And oh, that was supposed to be B cubed. It came out as B times 3. So that should be B cubed. And then 1 times B to the 4th. So this is a way to calculate a binomial expression raised to a power if you don't want to memorize all these formulas. Technically, you could also memorize. In the way that this is the formula for the perfect square of a binomial, this is the formula for the 4th power of a binomial. And you could just memorize all of them if you like, or you can memorize Pascal's triangle. So let's talk about how to use this. We want to use Pascal's triangle to expand 2 minus 3x raised to the 5th power. So the first thing is we want to find the 5th power row. And you know that by, if you look here, the squared row has the 2 in the 2nd position. The cubed row has the 3. The 4th row has a 4. And so raising to the 5th power is going to be this one. This is the one we're interested in right there. So our coefficients are 1, 5, 10, 10, 5, 1. Our A is 2 and our B is minus 3x. And we're raising it to the 5th power. So I'm going to say 1 times a to the 5th plus 5 a to the 4th b plus 10 a cubed b squared. Remember, as a goes down, 5, 4, 3, b starts going up. No b's, 1 b, 2 b's. 10a squared b cubed, 5a b to the 4th, b to the 5th. Okay, so I've got 1 times 2 to the 5th because a is 2, plus 5, 2 to the 4th times negative 3x, plus 10, 2 cubed, b is negative 3x squared, plus 10, 2 squared, negative 3x cubed, plus 5 times 2 times negative 3x to the 4th, plus 1 times negative 3x to the 5th. Okay, so I agree that is not the most beautiful looking thing, but compared to multiplying this out, and keep in mind this would be 2 minus 3x times 2 minus 3x times 2 minus 3x times 2 minus 3x times 2 minus 3x. You'd have 5 of them. That would be a lot of work, and this is going to simplify your work a lot. Okay, it helps that I know that 2 to the 5th is 32, so this is first term is 32. I happen to know that 2 to the 4th is 16, so this is 5 times 16 times negative 3. Where's my calculator? So 5 times 16 times a negative 3 is negative 240x. Okay. then this is going to be 10 times 2 cubed times the quantity negative 3x squared. So this is going to be 80, 10 times 2 cubed, 10 times 8, times, this is going to be 9x squared. 10 times 2 squared, 10 times 4 is 40, times negative 3 cubed is negative 27x cubed. Then this is going to be 5 times 2, which is 10. Now 3x to the fourth is going to be 81x to the fourth. It's positive because that's even. And the last one is just going to be, and I don't happen to know this one, so negative 3, let's see. Let me do it so you can see. Parenthesis negative 3 raised to the fifth gives me minus 243x to the fifth. Okay, so 32 minus 240x. 80 times 9 is going to be 720x squared. 40 times a negative 27 is going to be negative 1080x cubed plus 810x to the fourth minus 243x to the fifth. Ugh, that is a lot. And granted, that's not necessarily the most fun you might have ever had in your life. But if you try to imagine how miserable this would be multiplying it out, because you would get these same values, but you would also need to be combining like terms. The really brilliant part of this is that you don't have to, all the terms are combined for you. So it's kind of a no muss, no fuss. And it only works, though, if you've got two terms inside and you're raising it to an integer exponent or integer power. But that's the helpful bonus math, and it's kind of cool. If you want to look more into it, look up the binomial theorem, because the binomial theorem goes further than this, and it actually says you can find each of the individual terms separately. You don't have to use Pascal's triangle. There's a completely different way to do it. So using the binomial theorem, instead of having to draw and keep going, like if I asked for the 10th, you would have to keep going. Using the binomial theorem, you wouldn't have to come up with the rest of the Pascal's triangle. You would just have the numbers like that. So there's a lot of really cool stuff going on here, and then it starts to be related to statistics and probability, which is pretty cool. And if you ever have any questions, feel free to ask. Woohoo! That's your bonus math of the day. Yay! So you're awesome and amazing, and Pterodactyl thinks you're awesome and amazing, and math on, and woohoo!